2 minutes, guys, 2 minutes. All right, it's 12:30. Let's get started. Let's get started. Lord, thank you for bringing us together this afternoon. Thank you for everything that you do for us. I pray that you would continue to watch over us, that you would continue to bless us, should help us to stay focused and motivated for the remainder of this semester. For 1 month left, help us to finish strong. In your name we pray. Amen. Okay. All right, so what are we doing today, right? What are we doing today? Well, let's start with this, right? Final, initial, Laplace response. Final is the end, initial is the beginning. Laplace is a mathematician, and response is like the answer to something, right? So those were helpful, and I'm glad I could be there to give you those, right? All right, so I'm assuming that this has to do with final value theorem and initial value theorem, right? Final value theorem gives us the ability to test a system in the Laplace domain such that we can figure out what the steady state value is, right? The limit as s goes to 0 of s times f of s is the final value theorem. The initial value theorem allows us to know what the initial value of the system is, right? So the system at some time 0 plus. This is the limit as s approaches infinity of s times f of s. Laplace is like it's a whole the definition of a Laplace transform is the integral of a function of time multiplied by by e to the negative st if we evaluate that integral between 0 and infinity. Right? That is what it is. Okay? That's what it is by definition. We're going to talk more about responses today, so I'm going to hold off on that one. I'm going to hold off on that. You guys have any other major things that you want to talk about right now before we start talking about some other things? Okay. Give me a second, Trevor. We're going to talk a little bit about the lab right now, and then I'll answer all questions, right? So let's talk about that lab. I heard there's a lab. Hey, a note on the lab. Okay. So what do we have? Right? We've got this system. It looks something like this, right? No, I'm going to call this Z just for fun. All right, so this is what we have. Right? We got something that looks like this. The cave also looks something like this right there. Right? Good. So we can do a bunch of models for this, right? We can model this a bunch of different ways. We can model the electrical components, right? Except that we don't have the resistance or the inductance or any of that, so we're not going to do that. We have a motor curve that's seemingly not helpful because it ties together torque and omega, which has nothing to do with the current whatsoever. We have, what else? Well, let me ask you this. What would you expect the output, like, what would you expect the position of block 1 to look like? Be sinusoidal, right? So can't we simplify this model to say instead where we have the same exact components, the same exact motions, except that instead of me trying to model what's exactly happening between the current and how this is rotating, can't I say that my input, well, I'm not going to put that there. My input is just some input position x naught. Yeah, awesome. Sorry, someone. Right. Okay, good catch. Can't we define this? So, all right, this looks weird, right? But remember, we've done a problem on a homework where we had this, right, for a single block, where this had some input, right, some x position, right, x, and the base was actually moving, right? And this was given as x in, right? So can't we just say that some sinusoidal motion is being applied to this, and that's, yes, there's a torque back there, but that torque, what is the point of that torque? That torque is going to cause the gear to rotate. That rotation is just going to create this sinusoidal effect, right? So what is our sinusoid? What does it look like, right? So here's my gear. I'm going to say this is my pin, point P, right? And I've got my bar attached right there, okay? This pin, as this rotates, right, will travel around in a circle, right? When we get to, let's say here, we'll call it P prime. I end up with my bar in this position, right? The total distance that this can move is then the diameter of this circle. I measured it. Right? This radius is 1/2 inch. So D is equal to 1 inch. This is also known as the stroke length, right? Imagine this was attached to a piston. How far does your piston travel? It travels by the stroke length. The stroke length is the diameter of that circle, right? Because it goes up and down, up and down. Yeah. Doesn't matter. It doesn't matter the direction, right? The motion is just going to be the same. All right, so if I give this a certain amount, so how is current related, right? Because I tell you the current in all these trials, right? So how is current related? Great, good question. Yeah, no. Right. How is current related? Well, the more current I give it, the faster it'll spin. But if I leave it at a set current level, the motor will stay at that speed, right? Will stay at that speed. Now, what is the symbol that we use for angular velocity? Omega, there it is, thank you. What is the symbol that we use for natural frequency? Yeah, but it's, once again, omega n, right? So omega. What are the units of frequency? What's the other one that's appropriate and not hertz? Radians per second. What's the units for angular velocity? Radians per second. They're the same. They're the same. Your sine wave will be moving with a frequency of omega, which is equal to the angular velocity. But that's not super helpful because I don't have any sensors on here that are going to tell me what omega is, right? So how do I figure out omega? Well, at steady state, if I apply a constant angular velocity here, all three of these will be oscillating at the same frequency because that's how frequencies work. The only thing that changes about these sine wave motions is the amplitude and the phase shift, right? Because they won't all be perfectly lined up if you laid them one over another, right? So what does this motion look like, right? Let's talk about that. All right, this is z in units of distance, right? And this is time. We'll say it's in seconds. Okay. And if we start at 0, right, at p, we say that p is 0. We start at 0. Every time we go one rotation, right, we'll have that. The height of this, the amplitude of this wave has to be d, right? The amplitude of my input has to be d. The frequency can be determined from the period. If you know the period, right, isn't frequency just 1 over the period? How do we find the frequency? From watching the video, figuring out what our peak to peak time is, right? So essentially figure out how long it takes you to do a complete cycle, right? Now, in terms of what we're trying to do for the outcomes of this lab, right? I want you to compare the model motion of this final mass, so what you modeled, versus what actually happened. Does this mean that you need to scrub the video frame by frame and complete a full-on profile of what actually happened? No, take the average position. Compare the average position of both of those sine waves and see what they are, and see how close you are. Percent difference, right? So it changes up how some of the models that I've been seeing are going to work, but it also simplifies a lot of it, right? Is this cool? Is this fine? Or is this legal? The answer to all of those is yes, right? And the reason is, think back to when we did the solenoid, right? We didn't care the first time what the electrical circuit was doing. We just cared that it produced an electromagnetic force. I know the outcome, right? I know the outcome of my wait, I'll get there. I know the outcome of applying the current. I know what the outcome is. It is a positional change that is sinusoidal. So use a sinusoidal input and you can model the other three blocks as you normally would. Okay. Comparing Z3 in your model to Z3 in the experiment for all of the cases that we ran. Right.
Okay, so we're not worried about power on the motor curve
Yeah.
If you use that word,
Yeah, so you can't use that curve for that. Well, you could, but you don't know. You don't know what the torque is, right? So you can't really do that. Right. So. So. Recreate this sine wave, right? What does this sine wave look like? D times sine of omega t. So your input will look like that. Okay? That's what you're using. Some of you may have noticed, others of you might not, so I'll tell you right now. It's on the next slide anyway. But the due date for the lab is shifted till Wednesday of next week. We're on the 18th. So, okay.
So is that like not, since it's not really a force, that's not going to get put into like the free body diagram equation or the SSR element? It's just going to be
That's just going to be your input, right? Right. So, right, you have your state space block. Right, you are going to have equations that are a function of x naught, right? Because x1 depends on x naught. Mm-hmm. I mean, if you really wanted to get technical, right? Isn't x1 and x naught the same thing? Right? I mean, the arm is connected. That gear is connected via the arm to the first part, right? This has to move. If I set distance as a cone, right? Okay. We have any other questions? Is it okay? It's Thursday. Yeah. Just, what's up? Oh, I don't have my my sound on my laptop, so it's not telling me when people come in. Sorry. Mm-hmm. Okay. If there's no other questions, then we'll look at this. Right, I changed it in LabCloud. It's changed on the slide, so it's double official. 18th. I will probably move the due date for Lab 3 by a few days to compensate, but everything else, because it is dependent on the exam, will stay the same. Okay? All right. You guys have any questions? Everybody got anything? All right. So let's pick up where we left off. And I don't think we'll get through all of this today. We'll probably get up to analysis of dynamic systems. So that means next week. So here's the plan, right? Here's the plan. Let's lay it out. We'll get through most of this today. Tuesday of next week, we'll talk about impedance and transfer functions. And we're going to kind of have a repeat of what happened the first few weeks of the class, where I'm going to post a bunch of examples, and we're going to try to do a bunch of examples next week. Okay? That's what we're going to try. Okay, inverse Laplace transform, right? So what is the goal? Right? Remember, I think I said this in your guys' class on Tuesday, but the goal of, right, the idea here is that we can take a Laplace transform, but that doesn't necessarily help us, right? Because once we have this in the Laplace domain, what are we supposed to do with it, right? How is that useful? And it's useful because it allows us to solve the differential equation using algebra. But then we need a way of pulling it back out into the time domain, right? So much like, Nightcrawler teleporting, right? It's one thing to go into the hellish dimension. It's another thing to be able to get out, right? So the overall goal is to use the Laplace transform to obtain the response of a dynamic system that's subjected to some initial condition, right? or a forcing function. So how? How do we do it? We're going to systematically attack this, right? And the process is first that we take the Laplace transform of every term in our ODE. Right? So where does this ODE come from? Great question. You guys ever heard of Dr. D's super terrific number one 5 steps for making models? You guys ever heard of that? No? It's too bad, because that's a really great framework for you guys for making first and second order ODEs that you can then take from Laplace transform, right? So I mean, from tip to tail, right? We make the model, which gives us an ODE, and then we can analyze it using Laplace transform. Right? So first thing we do is we take our model and we run it through our Laplace transform. Then, using the results from step 1, we solve the Laplace transform for the dynamic variable, in general known as y of s, but we can have other things. And then finally, we obtain the system's response by inverting our Laplace transform. Right? And so how do we invert it? Right? Well, it's very clear from this definition how we invert it. Right? We just write L to the -1, and then it just happens. Right? Well, not exactly. So the way that you do it is you match y of s, what you solved for with y of s, to what already exists in your Laplace transform table. Right? Because if you get out 1 over s plus 5, you should recognize, by looking at the Laplace transform table, that that is the Laplace transform of e to the negative 5t, which would make e to the negative 5t the inverse Laplace transform of 1 over s plus 5. Right? So the way Laplace transform works, right? I have the function in the left column. If I want to take the Laplace transform, I move to the right column. If I'm looking at things in the Laplace domain, in the right column, and I want the inverse Laplace, I can move to the left column, right? You're just going the opposite way. So it becomes a matching game, in a sense, right? It becomes a matching game in a sense. So let's do this through an example here, right? So I've got this model, 2y double dot plus 10y dot plus 12y is equal to u of t, and it has initial conditions of y of 0 equal to -1 and y dot of 0 equal to 0. And so by the slides that we put on the, by the last slide, right, I want to take the Laplace transform of this entire equation. I want the Laplace transform of the whole thing. Okay. So I'm going to take the Laplace transform of everything. But remember, right? The Laplace transform of the big thing is the sum of all of the Laplace transforms of the little things, right? As it says in our calculus textbooks. Right, we can use our Laplace transform properties, right? This is a linear operator, and so we can distribute it. And so really, right, and I'm gonna color code these for a sec. Really, what we want is the Laplace transform of 2y double dot, right? Well, we can use another property here, right? Because if that's a constant, I can pull the constant out of my Laplace transform, right? So it's just 2 times the Laplace transform of y double dot. Well, going back to Tuesday's class, there were a couple of properties that are boxed in red, right? But if you didn't remember those, that's fine, because you have your master sheet, right? And Laplace transforms under differentiation, right? The second property listed, we are given this definition, right? L of d to the n over dt to the n of f of t is equal to s to the n f of s minus s to the n minus 1 f of 0 minus s to the n minus 2 f dot of 0 minus dot 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 minus f to the n minus 1 of 0. Okay. Lengthy definition. Right? We have a second order derivative. So what is this telling us? If I want to take the Laplace transform of the derivative of a function, I can use this, right? So if I have a second order, n should be 2, right? So let's do this for n is equal to 2. Right? D squared, well, this is going to give me what? Well, s squared f of s minus s to the 1 times f of 0 minus s to the 0 f dot of 0. That is the Laplace transform of the second derivative of y. So what does that look like for us, right? Well, this is going to be 2 times s squared y of s minus s times y of 0 minus s to the 0, right, which I'm just going to leave as 1, times y dot of 0. Okay. Well, great. Let's plug some things in, right? Because I know y of 0 and I know y dot of 0, right? Those were given. So this is just equal, I'm going to multiply through by 2 at the same time. So we've got 2s squared y of s minus s times, well, y0 was negative 1, so this is going to be plus 1s minus 0.5, right? But I got to multiply through by 2, right? So it's plus 2s plus 1. Okay. Right, all right, so I did 2 things at once. This is negative 1. This is 0.5. I multiplied through by 2. It should be negative. Good catch. Good catch. Okay. Sign errors withstanding. Right, this is how we do it. What's the next part? Right, well, I need the Laplace transform of 10 y dot. Well, same deal. I'm going to pull the 10 out. Well, this time, right, this time, if I'm looking up here, right, like this, I'm going to say d to the 1, right? So I basically just end up erasing those terms, and that's going to be the first derivative term, right? So we get s times y of s minus y of 0. Plug some things in, and you get this. I'm about to say something that's going to sound very foolish, but it's also very profound. I'm going to take the Laplace transform of 12y. The 12 comes out. The Laplace transform of y of t is the Laplace transform of y of t. It's just y of s. Right? That's what it is. Remember, what we're trying to do here, right? We don't know what y of t is. We're trying to find y of t. So leaving it as y of s, we're going to recombine all of this equation together And then we're going to solve for y of s, right? We're going to get one giant thing that's y of s is equal to a bunch of stuff, right? That's what we're looking for. Because eventually we're going to take the inverse Laplace transform of that stuff, right? And everyone will be happy and excited. They'll be dancing in the streets, right? All those things. All right. Finally, we need to take the Laplace transform of u of t, right? And what do we know about u of t? Well, u of t is 4 times capital U of t, right? And just as a refresher, right, capital U of t is my unit step, right? And the unit step tells me that we're equal to 0 for time less than 0, and we're equal to 1 for time greater than or equal to 1, right? That's what it tells me. So I'll ask you a question, right? Do we care about when the unit step is not on? The system response to nothing is nothing, right? So really, we have this unit step. We're only caring about when it turns to 1, right? When it hits 1, well, 1 is a constant, right? A step input is a constant. 4 times the unit step is just a step of 4. Whenever we hear that we have a step, we should automatically, in our brains, associate that with a constant input. What is the Laplace transform of a constant? You did it in class on Tuesday. It's whatever the constant is over s, right? So in this case, we have 4 over s, right? So the Laplace transform of u of t is equal to 4 over s. We have everything here. We have the Laplace transform of everything, right? We have the Laplace transform of everything. So we're going to recombine this equation on the next slide, right? And then we're going to algebra it, right? And I don't know if you guys can read my other camera here. You're at home, right? But it says whoever told you that you never needed algebra ever again was a liar, right? They lied to you, right to your face. Okay? We need algebra in a big way, like air and water. Okay. So, any questions so far? Everybody doing all right, right? So all we've done so far is we've applied a couple of our Laplace transform properties, right? That's all we've done so far. We distributed the Laplace transform to every term in the equation. We have taken the Laplace transform of a derivative, right? We made sure to apply our initial conditions, which we were given. That's important. So now what, right? Well, now I'm going to rewrite my equation, right? So I've got 2s squared times y of s plus 2s minus 1. Right, remember, this is that's the Laplace transform of 2y double dot plus 10s y of s plus 10 plus 12 y of s is equal to 4 over s. All right, so I've just substituted in the Laplace transforms for where they were supposed to go, right? Remembering that, remembering that all of this right here, this is my, not 12, this is my 2y double dot. This was 10y dot, and this was 12y. Right? That's what we have. So now the algebra fun begins, right? So what am I going to do? Well, I'm going to group all my like terms. I'm going to keep all my y of s's on the left side, and I'm going to move everything else to the right, right? So group my y of s's, move everything else to the right. And what do we get? Well, we get 2s squared plus 10s plus 12 times y of s is equal to 4 over s minus 2s minus 9. Why is it minus 9? All right. Well, look, I've got this 2s here, right? That's the only term with an s in it. So that moves over by itself. But I've got these two. I've got negative 1 plus 10, right, which gives me positive 9, but moving it over means that it's a negative 9 on the other side. Okay. I'm also going to apply a common denominator here. All right, so I multiplied each term by s over s. Well, the other two, not the 4 over s. Multiplied the 2s by s over s and the 9 by s over s. Right? Then I can add them all together. And that's fine because all I've done is multiply each of them by 1, right? That's all I've done. I haven't changed the value of either of them, but I allowed them to be manipulated in this way. And you're going to see that it actually makes things a lot nicer to have it in this format. Because now I can solve for y of s. Right? So I have to divide out by 2s squared plus 10s plus 12, right? And now I've got this. Now I've got this. Okay. Everybody following good so far? Yeah? Yeah? Any questions so far? Everybody doing all right? So now we take that and we go right to the Laplace transform tables, right? And we see, is there anything that matches this particular function in our Laplace transform table? So what do you guys think? You've had some experience with the Laplace transform table. Is this something that is automatically already in the Laplace transform table? It is not. So what do we do, right? We can't take the inverse Laplace transform and we go home. Right? End. Fiend. Short class, right? No. Right. I spoiled it right before, but we're gonna do the partial fraction expansion. Because why? Right? Well, this is why. That kind of looks like the characteristic equation in the denominator, right? This isn't a transfer function, but it looks like the characteristic equation. So I can factor this. Right? So let's do that. Let's factor this. And we're going to check our roots. I'm going to factor this. All right, first of all, what I'm going to do is I'm going to pull a 2 out of this, right? Because each of these will allow me to pull a 2 out. So I'm just pulling a 2 out front, and then you get s plus 2, s plus 3. So you pull the 2 out. Remember, when you factor it, you want to clear that squared variable, right? You want to clear that squared variable. that also has another benefit. Right, because also what I'm going to do is I'm going to divide every term on the top by 2 now to get rid of that 2 altogether. Now look at that. What do these roots tell me? Right? I've got a pole at 0, I've got a pole at -2, and I've got a pole at -3. Those are real distinct roots, right? What does my root response tell me when I have real distinct roots? Stable. Well, one of them's 0, right? So it's marginally stable. The other 2 are negative, right? What kind of response would you expect from each of the parts? No, underdamp's going to be complex conjugate roots, remember? That's where we get our sinusoidal and our exponential together. If I have real distinct roots, what's that going to give me? Yeah, what shape am I looking at? Exponential decay, right? So we're expecting an exponential decay here, and the s, that 0 root, is just going to give us a flat line, right? Because e to the 0 just returns whatever we multiply by, right? Okay. So we can do partial fraction expansion, right? So what does that look like here, right? So I'm going to rewrite this as 2 minus s squared minus 4.5 s over s times s plus 2 times s plus 3. And for real and distinct roots, and we'll go over this in depth in a minute, but just for now, we're going to do this. So what am I doing, right? I'm separating each of the root responses, right? I'm separating each of my root responses because remember, right, we've done this in differential equations. When we have a system with multiple roots, we end up with the sum of all the different responses, right? Same idea, right? We're taking this fractional term and we're splitting it up into the pieces, right? We're splitting it up into the pieces. So what do we do now? I'm going to multiply this entire thing here by s times s plus 2, s plus 3. And if I do that, I'm left with 2 minus s squared minus 4.5s is equal to a times s plus 2 times s plus 3, right? Because the s cancels there, plus b times s plus 3, plus c times s plus 2. So I'm going to expand these terms, right? I'm going to expand these really quick. As squared plus 5as plus 6a plus bs squared plus 3bs plus cs squared plus 2cs is equal to this. Okay. So what do I do now? Right? This is great. What do I do now? Now I'm going to group all of my coefficients for my various terms here. So for my s squared terms, right, I'd have -1 is equal to a plus b plus c. My s to the 1 terms, I got -4.5 is equal to 5a plus 3b plus 2c. And for my s to the 0 terms, my constants, right, I've got 2 is equal to 6 times a. I've got 3 equations with 3 unknowns. I can solve these simultaneously. It's pretty easy to figure out what a is, right? A is a direct, a is just 1/3. Use your favorite method for solving these, right? I like to put mine in the calculator, have the calculator do it for me, right? But you can certainly, for a system of 3 equations, it's not a big deal to solve one in terms of the other and figure out, right? You got A, you plug A into both equations, solve one of them for B, plug B into the other equation, solve for C, plug that into the other, to the first equation, right? And solve for C, right? Not a big deal. Once we have A, B, and C, right, which I'll write down on the next slide, I'm just trying to give everybody some time to copy this. Once we have A, B, and C, then we're cooking, right? Then we're cooking. Okay. So if we solve those simultaneously, A is 1/3, B is -3.5, and C is 2.17. So what do we know, right? Well, from the previous slide, we know that y of s has to be equal to a over s plus b over s plus 2 plus c over s plus 3, right? That's the partial fraction that we split it up into. So I can plug in a, b, and c here, right? And if I do that, I will get 1/3 times 1 over s plus, well, let's just do it this way, minus 3.5 times 1 over s plus 2 plus 2.17 times 1 over s plus 3. Now, I want you guys to look in the Laplace transform tables and tell me what time domain function would you use to get the Laplace transforms that are on the right-hand side of this equation, right? Because I need to take, I'm going to, so I want y of t, right? I'm going to take the Laplace inverse of this. So what's the inverse Laplace transform of 1/3 times 1 over s?
Would it be 1/3?
All right, so I've got two different answers, which is obviously going to lead to a fight to the death, as are the rules of college. So somebody said 1/3, somebody said 1/3 e to the negative t. Is that what it was? Nobody saying that? No. All right, so who thinks it's 1/3? Right. He thinks it's 1/3 e to the something t. It's 1/3. Good job, Blake. Right, remember, 1 over s. 1 over s is a constant, right? 1 over s becomes 1. Times 1/3 is just a third. What about the second part? Negative 3.5 times 1 over s plus 2. What does that become? There it is. Negative 3.5 e to the negative 2t. What about the final part? There it is. 2.17 e to the negative 3t. And there it is. That's the time domain response for our system. If we had to do this with differential equations for a second order system, it's not that bad, right? It's not, you could do it. The main time saver here is that partial fractions inevitably takes less time than using the initial conditions to solve for your constants, right? Because one derivative is not that bad. But if you have a third order system, you've got to take the derivative of the system twice, fourth, 4 times, and so on and so forth for however many order system you have, right? The utility of this really is exceptional when we start talking about higher order systems, right? And how can we analyze really high order systems very quickly, right? Because we just do some algebra and partial fraction expansion. Okay. So that's the process, right? We take our model, we take the Laplace transform of the whole thing. We solve it for the dynamic variable of interest. We do partial fraction expansion after we check the roots. And then we check the table to see if we have an exact match. That's what we do. And you are looking for an exact match. If it's not an exact match, we have to sometimes massage Laplace transforms into the correct form, right? We'll talk about that in a little bit. You guys have any questions on this? Right? Yeah, sure. The question was, if we have a bunch of separate systems, like an electromechanical system, and would we have to combine the equations into like a master system-wide equation to analyze it using a Laplace transform? And the answer is, it depends on what response you want out, right? And so potentially, but I will tell you this, once you move all of them, if you take the Laplace transform first, before you start to manipulate them, that's what you should do, okay? Because it makes it a lot easier to keep track. Like, you don't have to do integrals of variables, right? You'll just end up with s's and things over s, right? So everything becomes an algebraically manipulatable equation in the s-plane, right? And so we will talk about complex transfer functions going from like the motor, or going from like current through a motor all the way to moving something, where we want to know the transfer function between the current input and our torque output, right? And we can do that in Laplace, and it's a lot easier because you're just doing algebra, right? So this is another thing that lends itself well to that, right? Combining systems, which is also one of the reasons why I didn't want you guys to really do it before this, because you're just going to bang your head against the wall trying to keep tracks of integrals and derivatives of different things. All right. Any other questions? Partial fractions. You know, I believe that you guys have seen partial fractions before. I believe it. Oh, there's one more thing with this, right? We were given initial conditions, right? Why don't we test our initial condition? Y of 0. So if we plug 0 into this, we'll get 1/3 minus 3.5 plus 2.17. What does that give us? What's 1/3 minus 3.5 plus 2.17? I've been shown that it is negative 0.997. That's really close to -1, which is what our original initial condition was. Right, so it checks out. You could take the derivative of this and check the y dot 1 if you wanted as well, but we're not going to do that right now. Right, so there's a built-in check too, right? If your initial conditions don't come out to where you were told that they were at, then something went haywire, right? So let's really dive in a little bit more to partial fraction expansion. Right? Like I said, it's in my top 5 favorite expansions of all time.
Okay, is it like partial Fourier Laplace or
I mean, you can't, I guess I can't choose, right? I can't choose. We got partial fraction expansion, we got Taylor series expansion, right? The expansion of air in a piston, right? That's 3. That's 3 of the 5. You guys want the other 5? You got to come to class for the next 4 weeks, man. That's incentive right there. Speaking of incentive, next week we got to hammer out what you guys want as your incentive for exam 2. So think about it, talk about it, get back to me next week. All right, so partial fraction expansion was the key to our previous example, right? Without partial fraction expansion, we're dead in the water, right? What is partial fraction expansion? Well, by definition, right, we have this thing here where we can say, well, y of s is equal to a1 over s plus p1 plus a2 over s plus p2, where p is our pole, right? And all the way out to an over s plus pn. These a's, the a1, a2, an, those are known as residues. And that is the same thing that we were calculating, right? A, B, C, those are also the residues, right? Because it takes the same form here. But the thing that's different about this method, right, is that we can calculate the residues directly using AI is equal to s plus pi times y of s, and evaluating it at s is equal to negative p sub I. Okay. Now I want it to be known, the only reason that I'm going over how to do this with residues is because this is the book, right? The textbook uses the residues approach. I will continue to do them the way that I just did them on the board. That is how I do partial fraction expansion. They are equivalent methods. If you feel like you like one or the other, feel free to use whichever one you want. Okay? There. But the difference being that the partial fraction expansion with residues is in the book, and at 11 o'clock at night, you're not going to be able to get hold of me, but you sure as heck will be able to get hold of your book. Okay? So that's the difference. Now, I got Among Us games to play. I can't be doing work at 11 p.m. Unbelievable. All right. So let's highlight this with an example. We'll do it both ways. I'll show the equivalence of these methods. Okay? Show the equivalence. So look, we've got y of s is 2s plus 5 over s squared plus 8s plus 12, right? So you see that, and your gut instinct is, you know what? I gotta check those roots, right? I know that's what you're all thinking. So let's do that, right? Let's factor this. Let's factor this out, right? So I'm gonna have 2s plus 5 over s plus 2 times s plus 6, right? So I've factored this. Now, I didn't go over it in the last example, but in case we're a little bit rusty of getting roots from this, right? If you factor it, right, and then I set each of those terms equal to 0 in the denominator, right, that will give me the root. Just in case there's anybody who's rusty with how to factor things out and get the roots, right? All right, so my roots here are -2 and -6, right? Or as some people say it, I've got poles at S equals -2 and -6. Great. Fantastic. So those are both distinct real roots. So we can just do the same thing that we did before. We'll have as A over S plus 2 plus B over S plus 6, right? If I multiply the whole thing by S plus 2 times S plus 6, right, I'll get 2S plus 5 is equal to A S plus 6A plus B S plus 2. That is what I will get. Right. Okay. Okay. So we do the same thing again, right? We're going to say, well, I'll grab all my S terms and I'll grab all my not S terms here, right? So my S to the 1 terms tell me that 2 is equal to A plus B, and my S not terms tell me that 5 is equal to 6A plus 2B, right? Solve these simultaneously, and I get A is equal to 1/4, and B is equal to 7/4. Let's check it. 2 is equal to A plus B. 1/4 plus 7/4 is 8/4, or as some people call it, 2. 7/4 plus 1/4. Don't sass me, Trevor. Don't sass me. You think I would make mistakes when my lectures are on the internet? Come on, please. Everything on the internet is 100% true all the time. Jeez. Okay. So we can take A and B, we can plug it back into our partial fraction, right? So we'll get y of s is equal to 1/4 times 1 over s plus 2 plus 7/4 times 1 over s plus 6, right? So that means that by the virtue of an inverse Laplace transform, right, I've got y of t is equal to what? You guys tell me. What do I got here? Use the table. Oh, also, I will be posting the full version of the Laplace transform table some point today or tomorrow, just so you guys have it.
1/4 e to the -2t plus 7 over 4 e to the -6t.
Indeed. Great success. This camera, also this camera. Multiple cameras. I'm thinking about asking the school to get me one of those scorpion chairs that has like the triple monitors that come down over the top. Then I'll put a capstone next year, have somebody put it on like a nice navigation system for me. So I just basically sit like Professor X in my scorpion chair. All right, anyway. Okay, so that's the first way, right? We can also do this with the residue method, right? So how does that work? Right, how does that work? Well, residues, right? So if we're going to do this with residues, remember we already came up with the partial fraction expansion looks like A1 over S plus 2 plus A2 over S plus 6, right? That's, instead of A and B, we're using A1 and A2, right? That's what we have already. So if I want A1, right, by the equation that we just looked at, A1 is equal to S plus 2 times Y of S, evaluated at S is equal to negative 2. Okay? So this is what? Well, this is S plus 2 times S plus 2 over S plus 6, right? So S plus 2 over S plus 2 times S plus 6, right? And the numerator was 2S plus 5, right? Well, these cancel. So I'm left with 2S plus 5 over S plus 6. And I'm going to evaluate that at negative 2, at S is equal to negative 2. And if I do that, well, 2 times negative 2 is negative 4 plus 5 is 1. Negative 2 plus 6 is 4. So A1 is equal to a quarter. Oh my goodness. It's equal to the same thing that we got in the last one. Heavens. What about A2, right? Well, A2 is the same thing except we're going to use the other pole, right? And we're going to evaluate it at negative 6. So we get S plus 6 times 2S plus 5 over S plus 2 times S plus 6. Right? These will cancel. We'll set S equal to negative 6. Well, that's going to give me, well, negative 6 times 2 is negative 12 plus 5 is negative 7. And negative 6 plus 2 is negative 4. Negative 7 over negative 4. Last time I checked, that's the same as 7 over 4. So once again, great success, right? Then what do? Well, then we take these, right, and we plug them back in to this equation up here that we started with, right? And guess what? We have the same partial fraction expansion. Those residues were the same as A and B. So, you know, as Blake told us, right, it's just this. Right? If you guys can believe Blake, that's what it is, right? So Y of S original, right? So Y of S is equal to this, right? But Y of S is also equal to that, right? Yeah. Okay. All right. So that's real distinct roots, right? You know how to handle real distinct roots. So anything that's just got a real portion. Great stuff. Does anybody have any questions about real roots, real portions of roots? Remember, we know what the roots are, so we understand what the response should look like, right? It feels kind of like cheating a little bit, right? But it's not. You paid for a bunch of classes that you took before you got to this class. You should use some of that knowledge that you got, right? You have these skills already built up. We're just building on top of them and using them in a slightly different way. So when we do these partial fraction expansions, we shouldn't really be taken by surprise for first and second order systems, because those are very well characterized, right? Those are very well characterized. So we understand what the form of the solution should look like. What we're really using this for is to figure out, right, what are the coefficients that go in front of my exponentials, right? Okay. So guess what? You can do this in MATLAB. Or you
can get the residue. You can check your residues with that. So you can check your residues in MATLAB. The code here, right, computes, whatever. I don't even know if that's a real word, but that's cool. It will find the residues, the poles, and the direct terms of the partial fraction expansion, or the gain, K. Right, so APK equals residue, numerator Y, denominator Y. What is numerator and denominator? Well, that's the coefficients of your numerator and the coefficients of your denominator. The same way you would define them as if you define them for the Laplace transform function, right? When you use, or the transfer function code that we used, right? The TF code. Okay. And that'll just give you your residues, your poles, right? And your direct term. So what about partial fractions with repeated roots? Like we talked about independent roots, right? What about repeated roots? So hey, check this one out. Right? 2s plus 8 over s cubed plus 7s squared plus 16s plus 12. Right? I can factor that. I'll get s plus 2 times s plus 2 times s plus 3. So we got two repeated poles at s minus 2 and s equal to minus, and one distinct at s equal to minus 3. So how am I going to handle repeated roots? We'll do our partial fraction expansion. And this is what the partial fraction expansion looks like for repeated roots. So we got a over s plus 2 squared. So you got to take into account both of them, both roots at once. You have to take into account just one of the roots, and you have to take into account the third root. Because there's a third root there. If you take, so you can take the inverse Laplace transform without finding A, B, and C, right? You can. It would just be in terms of A, B, and C, right? So if I take the Laplace transform of this, what do I get? And if I look at my Laplace transform table, and these should match up, but I'll get A times T, e to the negative 2t, plus b e to the negative 2t, plus c e to the negative 3. You can also do residues for this, but the process is a little bit different for repeated roots. So here's residues, right? Here's my residues. So A1, s plus 2 squared, y of s. A2, you take the derivative with respect to s, of essentially of A1, right? Of s plus 2 squared times y of s. Right, so you're looking at the effect of both roots together, and then taking the derivative allows you to separate one of the roots out. And then the third one's just the same as we had before. You can do the partial fraction expansion here now that we found the residues. Right. We fill in what A1, A2, and A3 are. Okay.
Okay. Any questions on repeated roots? No? All right. Well, we're gonna watch a video.
Everyone, welcome back. So today we're going to take a look at a problem with partial fractions, and specifically how to use these partial fractions to compute Laplace inverses. So just as a warm-up, we're asked to recall what the formula is for the Laplace transform of f prime in terms of the Laplace transform of f. In the second part, we're asked to find the inverse Laplace transform for three different functions. The first one is 1 over s squared minus 4. S squared divided by s squared plus 4, e to the minus 5s divided by s squared minus 4. And notice how we don't have any of these formulas, or sorry, none of these functions appear in the lookup table for a Laplace transform. So in each case, we have to use partial fractions to convert it or massage these functions into something which we do know the Laplace transform inverse for. And then lastly, for the third problem, we're asked to write down the partial fraction decomposition of this function 1 over s squared times s squared plus 4 times s plus 1 times s plus 3. And specifically, when we do the partial fraction decomposition, we're just going to leave the coefficients, the undetermined coefficients unknown. We're not actually going to solve for them. Okay, so I'll let you think about this problem, and I'll be back in a moment. Hi everyone, welcome back. Okay, so for part one, we're just asked to recall the Laplace transform of f prime in terms of the Laplace transform of f. So the Laplace transform of f prime we can write down as s times the Laplace transform of f, which I'll use capital F, minus f evaluated at the lower bound of the Laplace transform integral, which in this case is just 0 minus. Okay, so this is just part one. This is a warm-up problem. For part two, we're asked to find the inverse Laplace transform for three different functions. The first one is 1 over s squared minus 4. And we see here that we can factor the denominator into 1 over s minus 2 times 1 over s plus 2, which means that we can use a partial fraction decomposition, which has the form of a times, or divided by s minus 2, plus b divided by s plus 2. And now we need to solve for the coefficients a and b. So one way to solve for the coefficients a and b is just to multiply both sides of this equation through by the factors s minus 2 and s plus 2. We can then plug in values of s and solve for a and b. There's another way, which is sometimes referred to as a cover-up method. And in this case, what we do is we pick, for example, say one of the places where the denominator blows up. So for example, if we look at this factor s minus 2, this factor diverges when s approaches 2. So then what we do is we go back to our original function. We cover up the term s minus 2 where it diverges, and then in the remaining term, we plug in the value of s, which causes the factor s minus 2 to diverge. So in this case, s minus 2 diverges at 2, so we would cover this factor up and then plug in s is equal to 2. And this would give us the value of a. So for this problem, a is equal to 1 over 2 plus 2, which is just 1 over 4. For b, we look at plugging in s equals negative 2. So we cover up the factor that diverges in the original function, plugging in s equals -2 gives me -2 minus -2. So b is just -4. So this function is 1/4 1 over s minus 2 minus 1/4 1 over s plus 2. And when we take the inverse Laplace transform, so the inverse Laplace transform of 1 over s squared minus 4 is going to be 1 over 4. The inverse Laplace transform of s minus 2 is e to the negative 2t minus, plus 2t. The second factor is negative 1/4 e to the negative 2t. And this concludes the first problem. For the second function, we have s squared divided by s squared plus 4. So again, this function is not in the correct form to use a Laplace transform lookup table. But what we can do is we can divide long division of polynomials, the numerator out by the denominator. So when we do that, we end up with 1 minus 4 divided by s squared plus 4. So when we take the inverse Laplace transform of s squared divided by s squared plus 4, we're left with the inverse Laplace transform of 1 minus the inverse Laplace transform of 4 divided by s squared plus 4. And if we use our lookup table, we know that the inverse Laplace transform of 1 is the delta function. Meanwhile, the inverse Laplace transform of some number divided by s squared plus 4 looks like sine of, in this case, sine of 2t. Now, we needed 2 upstairs, so this is going to give us 2 times sine of 2t. And I obtain this by noting that the Laplace transform of sine omega t is equal to omega divided by s squared plus omega squared. So that's how I went from this formula, or this function, this Laplace transform inverse, to 2 sine 2t. Lastly, for part 3, the third problem, we're asked for the inverse Laplace transform of e to the minus 5s divided by s squared minus 4. Now note that we already know the inverse Laplace transform to 1 over s squared minus 4. In this case, it's just we're just multiplying 1 over s squared minus 4 by e to the minus 5s. So we can use the shift formula in addition to what we already computed, the inverse Laplace transform to 1 over s squared minus 4, to compute this inverse Laplace transform. So the shift formula says that we need to multiply by the step function t minus 5. So we're shifting with the step function. And then what we do is we want to shift the inverse Laplace transform of 1 over s squared minus 4. So the inverse Laplace transform to 1 over s squared minus 4 is 2t minus 5. So if we shift t by 5, we end up with 1/4 e to the 2t minus 5 minus 1/4 e to the minus 2 t minus 5. So again, just to reiterate, when we have an exponential e to the minus, say, 5t or 5s, and we already know the inverse Laplace transform of everything else, we just multiply by the step function u, t minus 5, the same shift, and then wherever we see the t in the inverse Laplace transform, we just replace it with t minus 5 in this case. Okay, and now lastly, for part 3, we're just asked to write down the decomposition for this very large function, the partial fraction decomposition of this large function. So it's s squared times s squared plus 1 times s plus 1 times s plus 3. Let me just double check. S squared plus 4. Okay. And unfortunately, this function's going to be a little ugly. We're going to have a constant a divided by s plus b divided by s squared. So these first two terms come from this term right here. For the s squared plus 4 term, we're going to seek a c times s plus d. So we need both factors, cs plus d, divided by s squared plus 4. We have e divided by s plus 1, and then plus f divided by s plus 3. So just to associate each factor, or each factor in the partial fraction decomposition with the original function, I've just drawn some arrows. Okay, and then lastly, although I didn't state this in the original problem, we can also just write down the inverse Laplace transform of this entire mess. Without actually determining the constants, we can just keep the constants in. So if we wanted to compute the inverse Laplace transform, well, it would just be a, because inverse Laplace transform of 1 over s is 1, plus b, inverse Laplace transform of s squared is t, plus, now this part has two terms, cs divided by s squared plus 4. That's going to give us c times cosine of 2t. The d divided by s squared plus 4 is going to give us, well, we need to multiply upstairs by 2 and divide by downstairs by 2. So we get d divided by 2 of sine 2t. This term e is going to give us e times the exponential of t, negative t. And then f is going to give us, or the last term is going to give us s, f times e to the minus 3t. Okay, so just as a quick wrap-up in this.
No wrap-up. All right. So we're going to watch one more. One more, but different, right? So that recaps what we've kind of been doing. Now we're going to talk more about complex roots. So what happens when I have real and imaginary parts? Okay. Hold on.
This screencast will show how to solve equations in the Laplace domain, or the S domain, which contain imaginary roots, and allow us to put them back into the time domain. To accomplish this, we'll use the equation shown on the screen here. To show the fact that this system in fact has imaginary roots, all we have to do is recognize the s squared plus 4s plus 5 part, and realize that using the quadratic equation, if we look at the square root term of the quadratic equation, if this term is less than 0, that will tell us the fact that our roots are in fact imaginary. So when we do this, we have negative 4. So therefore what this shows is the fact that we have two imaginary roots. Processes which have imaginary roots are systems or processes which will oscillate in nature. From a mathematical standpoint, that represents the appearance of cosines and sines in our final solution. There are some processes such as swings and pendulums which naturally have this. However, most chemical processes do not have imaginary roots. Where we sometimes see the presence of imaginary roots in chemical process control is for some systems which are controlled using PID control, where it is possible to end up with imaginary roots. In fact, many tuning parameters take advantage of this fact and are tuned to ensure the fact that the process obeys quarter decay, which is an oscillatory response. Recall that systems with imaginary roots will have the form of a plus or minus bi. But the question now becomes is when we're trying to convert this from the Laplace domain to the time domain, what functional form should we have? And the best way to answer this question is to look at the Laplace transforms that are available. Looking at the transforms provided here, what you'll see is the fact that there are no I terms here, and the fact that everything is left in s squared plus omega squared or s plus b squared plus omega squared. So therefore, we don't want to solve these using the value I, which is equal to the square root of -1. So our focus here will be to leave things in s squared plus 4s plus 5 terms. In other words, our focus is going to be looking at the last two equations I've shown here in order to eventually take the inverse Laplace transform. To do this, what we're going to have to do is use partial fractions. So what we'll do here is just rewrite what we have above and then break it into its roots. And what we'll have here is a over s, but we don't want to break the other root because of the fact that we don't want to deal with i's, because the i's provide us no help in trying to use the Laplace transform table. But what this means is that the numerator of this will not just be a constant, but it'll be of the functional form bs plus c. To solve for a, b, and c, our focus will shift to the numerator. What we'll now do is find a least common factor and multiply the a by the s squared plus 4s plus 5 and the bs plus c term by s, of which this must equal the numerator we already have, 3s squared plus 5s plus 5. We'll provide that here. What you'll notice on the right-hand side is that the highest power of s that we have is s squared. So what we now want to do is break this down into terms with varying powers of s, and we have three of them here. We have s squared, we have s to the first, and we have s to the 0. In other words, the constant terms. So if we look at our right-hand side, we see that we have an as squared term and a bs squared term. If we look at our s terms, we have 1 for a, 4as, and we have 1 for c, c times s. For constant, the only one we have is 5a. We then use the left-hand side to match what these coefficients have to equal. So if we look on the left-hand side, we have 3s squared, 5s, and 5. We can now solve for a, b, and c. First, we'll start with the s to the 0th equation to find a. A equals 1. We can then substitute in a equals 1 to the s to the first term, and that will show that c also equals 1. And the s squared equation will allow us to solve for b. b equals 2. Now that we have solved for all of these constants, we can substitute them back into the equation shown above. When that substitution is done, the equation is the one shown here. The inverse Laplace transform for 1 over s is relatively straightforward. It's just the inverse of a step function, which is just a constant. That's 1. In order to take the inverse Laplace transform of the second term, we have to go back to our Laplace transform sheet. As noted before, our focus here will shift on the bottom two equations because we don't have a perfect s squared plus omega squared in our denominator. But what we now need to do is find b and omega. In order to do that, we have to complete the square of the denominator. So in order to complete the square, s squared plus 4s plus 5, in order to complete that square, what you do is you take half of the value for the s term, which is 4, and then take the square of it. So therefore, that would be s squared plus 4s plus 4. You then add or subtract whatever the difference is with the original constant you had. So therefore, originally we had a constant value of 5. We already have taken up 4, so therefore what we're left with is 1. The s squared plus 4s plus 4 will be a perfect square. In this case, it'll be half of the value of the constant, which was 4, so therefore this will become s plus 2 squared plus 1 is our new denominator. By mapping this to the Laplace transform sheet, we've shown the fact that b is 2 and that omega is equal to the square root of the constant term hanging outside, which in this case the value is 1, so the square root of that is also 1. But looking at this, we hit a little bit of a problem. If we are to substitute omega and b in, what we have is 1, and for this part here, we have s plus 2. The problem is that our numerator for this is 2s plus 1. So what we're going to have to do is find a way to turn 2s plus 1, our numerator, into a linear combination of the 1 and the s plus 2. There are a number of ways to approach determining what the constant should be in front of the two terms found in the Laplace transform sheet. One will be provided here. And the methodology works very similar to the concept of partial fractions, where we're having a linear combination of multiple terms such that the numerators are consistent. The easy thing here is the fact that they both have the same denominator, so we don't have to worry about that step. So if we look at what we have here, we have that 2s plus 1 is going to equal a plus bs plus 2b. By looking at this, we see the fact that the only s term on the right-hand side is bs, so therefore that tells us that b equals 2. And what's left with the constant terms is that a plus 2b equals 1, which means the fact that once we substitute in what b is, that tells us that a equals -3. So if we revisit our original equation, with the second term factored out to be more friendly for the Laplace transform table, we can see that when we take the inverse Laplace transform of our second term, that just corresponds to the sine term that we have here. So therefore this term becomes e to the negative bt, where b has been shown to be 2, multiplied by the sine of omega t, where here we showed that omega was 1. And then we include the constant -3. So for our third term, it will correspond to the cosine term, which will be e to the negative bt, which is still 2, multiplied by cosine of omega t, which in this case is still 1. We then add the coefficient to our system, and when we put these all together, we get our final answer, which is that y in the time domain equals 1 minus 3e to the negative 2t sine t plus 2e to the negative 2t cos t. So an important part of dealing with imaginary roots is that you ensure the fact that when you're trying to solve the problem, you are gearing it towards the Laplace transform sheet that you have available. Different transform sheets may show things in slightly different ways, so you're going to want to gear it towards the Laplace transform sheet that is available to you.
Okay, right, so partial fraction expansion for complex roots, right, complex poles. Turns out, like how we showed us in the video, sometimes you have to do nested partial fraction decomposition to get the roots, right, to get them, or to get your residues. Right. So let's try this one, right, let's try this one. We have 2s plus 9 over s squared plus 6s plus 25. If I factor the bottom, what do I get? Well, what are the roots, right? What are the poles for this system? What are the poles? What are the poles of this system? Or if you solve this with the quadratic equation, what would you get out? What would you get out? What's that? -64. No. We solve for the roots, what would we get? There's a hint in the title of the slide. You should probably be getting something that's complex, right? Because Otherwise, talking about complex poles with doing an example that doesn't have a complex pole is probably poor form on Dr. G's part. Although I wouldn't put it past him, because I heard that guy's a jerk. All right, so what do we got? Yes. Yes. -3 plus or minus 4j. All right, so if you got these roots, if this is in fact a characteristic equation and you saw these roots, what type of response would you expect from seeing this? Or something? What? Yes. It is an underdamped, right? You would get some decaying sinusoid, right? And we know that going into this, so we should expect to get that out, right? So what are we going to need to do here? We're going to need to complete the square, right? Because as he said in the video, having I or J in the denominator doesn't help us, right? It doesn't. So let's complete the square here, right? If I'm going to complete the square on S squared, right? So plus 6S, well, I take half of it and I square it, so plus 9 plus 16, right? That's the same thing as S squared plus 6S plus 25, right? Just rearrange. But it has the added benefit of also being this. Why are we completing this square though, right? Well, because we know that it is a damped sinusoid, we can look at the sine and the cosine damped terms from our Laplace transform table. And we notice that both of those require us to have this completely square type of denominator, right? Now, which one is it? Is it sine or is it cosine? Well, in general, right, when we're doing differential equations and we say that we have some sinusoidal input, right, we typically say, well, the output is, the amplitude, some new amplitude times that sine function of omega t plus phi, right, where phi is my phase shift. That's typically how we would address this. But what is phase shift? Phase shift is just saying, well, I've got some of this that doesn't line up, right? So isn't a sine wave just a shifted cosine wave and vice versa? So really, we're going to take a sine wave and a cosine wave and add them together. So this has aspects of both, right? This has aspects of both. Okay, so where do we go from here, right? Well, we look at these transforms, we look at how these are structured, right? Well, in the denominator, I can already see that A is equal to 3 and omega is equal to 4. Right? Is everybody following me on that? You look at the denominator, right? You look at the denominator in both places, right? Right? That's what we've got. Okay, so we've got A, we've got omega. Now what? Well, now we have to figure out what percentage, essentially. We have to figure out how these scale. Right? We have to figure out how these sines and cosines scale. So let's rewrite what we have, right? We had y of s was equal to 2s plus 9 over s plus 3 squared plus 4 squared. And I'm going to say that this is equal to a times, what do I want? This is going to be A times S plus 3 over S plus 3 squared plus 4 squared plus B times 4 over S plus 3 squared plus 4 squared, right? So what is this doing, right? This is telling us that I've got some cosine term, and this one over here is due to my damped sinusoid, right? I've got a damped cosine and a damped sine wave. So what I've got. If we do partial fraction expansion, right, like we've just done, right, we're multiply through by that denominator. They all have the same denominator, right? So if I multiply through by S plus 3 squared plus 4 squared, I'm just left with 2S plus 9 is equal to AS plus 3A plus 4B, right? Because multiplying through by S plus 3 squared plus 4 squared cancels everywhere. So I can group my terms. Right. My S to the ones, I've got 2 is equal to A, jackpot. S to the 0, 9 is equal to 3A plus 4B. Well, A is equal to 2, right? So this is just 9 is equal to 6 plus 4B. And so B is going to equal 3/4. I just added the e to the negative bt. At, I guess, from our table. Doesn't matter. Okay, so now what? Now we plug it back in, right? Now I can say, well, y of s is equal to 2 times s plus 3 over s plus 3 squared plus 4 squared plus 3/4 of 4 over s plus 3 squared plus 4 squared, right? I can take the inverse Laplace of this now because I know s plus 3 over s plus 3 squared plus 4 squared is e to the negative 3t times cosine 4t times 2. Did I give myself another slide? No, I did not. Bummer. Okay. All right. So I just grab these off of the table now, right? So y of t is 2 e to the negative 3t cosine 4t plus 3/4 e to the negative 3t sine of 4t. Or if you want to get really fancy, right? 2 times cosine 4t plus 3/4 sine of 4t, everything times e to the negative 3t, right? If you're feeling fancy, right? Both are fine. Again, we know what it's supposed to look like. Make it look like what it's supposed to look like. Right? You know the roots. You know what the response is supposed to be. Right? make it look like that. Now, in some cases, depending on what your input is, you might get a higher order system, or you might get a third or fourth order system, depending on what your input is sometimes, right? We've already seen that a step input adds an order, right? Step input adds an extra root. So that sometimes happens. It also could happen that you have like something like the lab system, right? Which is a sixth order system, right? And so you can see where partial fraction expansion can get hairy pretty quickly, right? But I would argue that a sixth order system in Laplace is much easier to solve than solving a sixth order system in differential equations. You guys have any questions on this? Hopefully this was more review than brand new stuff. Hopefully. No? Partial fractions. Top 5 expansions all time. Better than the NBA expansion, that's for sure. That's not even in the top 5. Definitely not the NFL expansion. Get that stuff out of here. Forget it. You have the Jaguars back. Thank you. I said it. Internet people. I apologize for that. All right. Have any questions? Well, guess what? We can do inverse Laplace transforms in MATLAB too, right? That's fun. So we use this symbolic toolbox, right? And to highlight this, we're going to do example 8.8 using MATLAB, which is, by the way, the example that we just did. All right, so we should get the same answer, hopefully. Okay. So much like when we did the Laplace transform, we need to use the symbolic toolbox, right? So in this case, I'm going to set up my symbol as S. I'm going to set up my symbol as S. Why? Well, because it's the Laplace transform, right? You're already starting with the Laplace transform. Then I'm going to set up my function, right? Y of S, or Y, capital Y, is equal to 2S plus 9 divided by S squared plus 6S plus 25. Defining the Laplace transform that I was given. Then I use Y is equal to I Laplace of capital Y. Now, it's not a new I, it's not a new Apple thing. There's no I Laplace. No, sad face from everybody, right? I really think Apple is losing out by not having an I Laplace, but alas, they don't have one. Stands for inverse Laplace. I know, that was a horrible joke. I know. It's fine. I live most of my life like this, okay? It's fine. All right. So I Laplace is the command, right? And then we use pretty if we want to. You don't have to, it'll still give you the answer. And you do all 4 lines of that code, you will get this. Now sometimes MATLAB's a little stinker sometimes. Right? MATLAB is a little stinker sometimes. And they'll rewrite this as 2e to the negative 3t, or they'll pull out the e to the negative 3t, like I did on the last slide. And so sometimes people come to office hours like, I don't understand why this isn't giving me the same thing. So make sure you're looking at where MATLAB puts its parentheses. That's what I'm going to say. Right. So you can check these things with MATLAB, right? That's nice. It's nice functionality to have. Bless you. Do we have any questions? Everybody doing okay? No questions. All right. Well, talk about how to analyze a dynamic system using a Laplace transform, right? That seems like it would be helpful. So we'll try that. All right. So I'm going to group our approaches into two different categories. First, we have applying the Laplace transform to the IO equation, and second, we have using the transfer function, right? So either you use the Laplace transform method, or you use the transfer function method. There are two methods, okay? The Laplace transform method is very much the same method that we just used, where we had our second order differential equation. We take the Laplace transform of everything, including our initial conditions, right? And we go from there. The transfer function method is slightly different because it assumes zero initial conditions. Okay? So we'll go over both of them, right? And we'll talk about them. So just to recap, if you are told to use the Laplace transform method, like on a homework or a test, you should use the Laplace transform method. If you're asked to use the transfer function method, you should use the transfer function method. Okay? If you're told to use a specific method, make sure you're using that method. Okay? Okay. So what are the basic steps for the Laplace transform method? Right, we did this. We take the Laplace transform of every term in our IO equation, including the input. This converts our ODE into an algebraic expression in the S domain. We then solve that expression for our dynamic variable of interest, often known as our output, right, y of s. And then we take the inverse Laplace transform of that using partial fraction expansion to get y of t, right? And we did that. We did an example where we did that. We didn't come up with the model, right? But, you know, we can come up with a model. We get the IO equation. We take the Laplace transform, right? We can do this from beginning to end using, I don't know if you guys ever heard of the Dr. D's #1 super terrific 5-step method for solving problems. I've heard it's pretty good for, you know, doing dynamic systems models. All right, so now, after we've been using them for about a month, I will give you the real definition of a transfer function. The formal definition. Transfer function g of s is defined as the ratio of the Laplace transform of the output, y of s, to the Laplace transform of the input, u of s, with zero initial conditions. If you're asked to find the transfer function of the system, and you're given initial conditions, you should summarily ignore them. If you try to do the Laplace transform, if you try to find the transfer function and you used initial conditions, it's not the transfer function, or it's not correct. So let's do a quick example here, right? Well, I've got y double dot plus 8y dot plus 10y is equal to 4u dot. Okay, great, fantastic. So I'm going to find the transfer function of this, right? So first things first, let's take the Laplace transform with zero initial conditions. Boom. There it is. And notice, when you assume zero initial conditions, something very interesting happens here. All of those go away. They'll go away. And what are we left with? S squared plus 8s plus 10. Is equal to 4s times u of s. Well, that's very interesting, right? Because when you look at the original example, the original equation, all you had to do was put an s squared in for the y double dot, right? S squared y plus 8sy plus 10y is equal to 4su, right? Not ASU, 4su, okay? And then, if you divide over the u of s, and you divide over the s squared plus 8s plus 10, you get the transfer function, right? Because the transfer function, the definition tells us that g of s is equal to y of s over u of s. Now, I want you to notice something about this. We don't care what the input actually is at this stage to make the transfer function. If you're told it's a step input, leave it generic as u of s, because the transfer function works for any and all inputs, okay? So like in the example we did, where we took the Laplace transform, right? If you're doing the Laplace transform method, then yes, take a Laplace transform of the input. If you are not, if you're doing the transfer function method, in order to find the transfer function, we assume the generic input u of s. Because later, when we want to solve this, y of s is just my transfer function times the Laplace transform of u of s. And that, when you're doing this, that's when you finally put in your input, right? We keep it general until we need to use it, okay? We keep it general until we need to use it, okay? What's the transfer function? What's the difference between a time domain transfer function and the Laplace domain transfer function? The d's and the s's, right? We already talked about that. Remember, when we have the transfer function, you automatically have the characteristic equation. Man, that one, I stumbled over that one. Characteristic equation of the system in the denominator, right? So if you found the roots of that, you have the roots of the system. Right? So how do we analyze something using a transfer function, right? Well, it comes down to our block diagram again, right? I have some input coming in. My input times my transfer function gives me my output. Right, so the basic steps would be we're going to derive our system transfer function from the mathematical model, right? Then we multiply the transfer function, g of s, by the Laplace transform of the given input function. Then we take the inverse Laplace transform in the same way that we did before, right? So you do partial fraction expansion, and you'll find what your system response looks like. Okay? So it's the same process that we went through before, right? Same process, but just a little bit different, right? Just with zero initial conditions. The same thing that we did, but with zero initial conditions. Transfer function is very powerful, right? It's very powerful. It allows us to test multiple responses quick and easily. You can come up with multiple transfer functions for a system, or just the one that goes from global input to global output. Remember, there are as many transfer functions as there are input-output pairs. Right? Remember that. Okay. You guys have any questions? You doing okay? All right. Let's try one. Figure shows a single disc mechanical system where a motor provides a torque T in directly to the rotor inertia J. We want to obtain the angular velocity response of this mechanical system if the rotor is initially spinning with omega naught equal to 120 radians per second, and the input torque is a step function of magnitude 15 Newton meter. The rotor moment of inertia is J equal to 0.4 kilogram per meter squared. And the viscous friction coefficient is 0.06 Newton meter second per radian. Okay. Cool. Cool. So what should we do? Should we start off with making a model? Well, in the interest of time, we're not going to run through the first 4 steps of the 5-step process. I'm going to trust that at this point in the semester, you guys can check me, right? And we are just going to talk about what the model is, right? For this particular system, which we've done a couple of times, we will get a model that looks like that. Right? It's a first order model with respect to the velocity. We told specifically that we want the velocity out, so we better have velocity as our output. Right, so I'm going to write that on the next slide. And we'll do everything here, right? So J omega dot plus B omega is equal to T in of T. And I'm going to take the Laplace transform, right? Remember, write this down, omega naught is equal to 120 radians per second. So I'm going to take the Laplace transform of this, right? The Laplace transform of J omega dot is going to give me J times omega of S times omega of S. The horseshoe looking thing, that's a capital omega. Remember, if we're doing the derivative property, right, you can look it up in the master sheet, but for the first derivative, it's S times the function, the Laplace transform of the function minus the initial condition of the function. I can plug some things in here, right? This is 0.4 S times omega of S minus 120 times 0.4, right, which is going to be 48. So omega naught was 120, 0.4 times 120 is 48. The Laplace transform of B omega is just B omega. And we're told that T in is just a step of 15. So this is just 15 over S, right? Because remember, this is the Laplace transform method, not the transfer function. So I can rewrite my equation here, right? I can get 0.4 S omega of S minus 48 plus B omega of S is equal to 15 over S, right? Group my like terms, 0.4 S plus B. Well, B was what, 0.06? Yeah. Yep. Times omega of S is equal to 15 over S plus 48, which will just be 15 plus 48 S over S. I can solve this for omega. And I'll have this. And then I'm going to pull the 0.4 out. I'm going to pull 0.4 out of that And I'll end up with 15 over 0.4s times 1 plus 0.15 plus 48s. And when I divide through by the 0.14, I'll get 120s plus 37.5 over s times s plus 0.15. That shouldn't be a 1, that should be an s. Sorry. Cool. What are my roots? What are my roots here? What's that, Trevor? You could. You could use roots, right? But given this denominator here, right? What are my roots? Yep, 0 and negative 0.15. Distinct real roots. Distinct real roots. You know how to handle that with a partial fraction expansion. So let's hope that I have another slide in here. There we go. So what did we come up with? Let's write down what we just had up here. We had omega of s was equal to 120s plus 37.5 over s times s plus 0.15. A over s plus b over s plus 0.15. Multiply the entire thing by the denominator. Right, if I do that, I'm left with 120s plus 37.5 is equal to as plus 0.15 a plus b times s. My s to the 1 terms come together. My s to the 0 terms. I can immediately solve for a, right, from this equation. A is equal to 250. I plug that back in here, and b is going to be negative 130. Which leaves me with this. Okay. So what's my inverse Laplace transform for this? What is omega of t? Right? Go to the tables. What do we got? What's the inverse Laplace transform of 250 times 1 over s? 250. What's the Laplace transform of negative 130 times 1 over s plus 0.15? There it is. Let's check the initial conditions. Plug in 0. 250 minus 130. What do I get? 120. Right? Which is what omega 0 was. So we're good. You guys have any questions? Any questions on that? No? Everybody doing all right? Okay. So, if there's no questions, we're going to play Jeopardy today. I know I said that we weren't going to, but then I changed my mind, so we're going to. So you're going to want to hop on Discord and communicate with your groups that way. It's probably the easiest way to do it. Let me give you the rules, right? You will get one Jeopardy song, well, say one to 2 minutes, right? To discuss how many points you're going to wager. I will show you your points in a second, and you can write them down, and then you can determine. All right. Once, also, I will tell you what the category is, so you're not just wagering blind. Right? But like the way that Final Jeopardy, right? That's how Final Jeopardy. Okay. Once your points have been locked in by entering in Discord what the points are, you will get to see the answer, and you will be given 2 Jeopardy songs to come up with your question, right? The answer in the form of a question, all that. Put your answer in Discord, and then that's it. It says I'll have you read them, but just put them in Discord, and I'll suss it out at the end. I'll tell you what the answer is, and then then I'll be good. All right, your points will get updated on Monday. All right, everybody clear on the rules ish. Taylor, put it in your team channel. In your team channel. In your team channel. Okay, ready? Everybody, somebody from your team, write down your points. How many points you have available for wagering. You can wager all of them. You can wager none of them. You can't wager negative points and then throw. That's not how this works, right? Okay. Everybody's seen their points. I will now give you, so I was going to play the Jeopardy song, but it's going to cause a massive amount of feedback and probably blow up the whole campus, so we're not going to do that. I'm just going to give you guys, 1 minute to place your bets. I mean, wouldn't you like to know? It's engineering. All right, 1 minute. 1 minute. Put your bets, your wagers. How many points do you want to wager on your knowledge of engineering? You can throw it into the Discord, into your team chat. Do, 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 do. Do, 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 do. Do, 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 do. All right. A few more, like 30 more seconds. Make sure it's very obvious. All right. Okay. 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 All right. Looks like all of the points have been wagered. The points have been wagered. What's that? Put it in your team chat. Put everything in your team chat. Otherwise, you're giving free answers, people. Unless the strategy is to put something completely wrong in there and see who does it, right? But yes, you need to answer in the form of a question, please. All right, let's see. One more. All right. All right. Here's your question or answer. The Eiffel Tower was built using 2.5 million rivets and 14 million pounds of this material. You have 2 minutes. 2 minutes to put your answer in to. No, that's not how Jeopardy works. One more minute. One more minute. Remember, form of a question. "30 seconds. When I say form of a question, that means like what is, who is. Not just your answer with a question. Also, if there's multiple answers in your chat, make sure you have one highlighted that you actually want to use. 15 seconds. Okay, 2, 1. All right, the time. Time is up. Let's see. Everybody's got an answer in? Okay, okay. It's looking like everybody's got an answer locked in. What is it? Oh. Well, no answer, guys. No answer. Give me a sec. I don't know why it's skipping the answer slide. That's really quite annoying. It is iron. It's iron. Fine. Yes. It is iron. Give me a sec. There we go. What is iron? What is it? Congratulations if you got it right. If not, next week we will have another question for you to buff up on. It won't always be engineering related. Might be literature, poetry, right? Anyway, that's it for me for this week. Going a little bit earlier-ish. Next week, we'll start talking about transfer functions and impedance. Okay, we'll talk about transfer functions and impedance, and then we'll do a boatload of examples. And hopefully, as many as we can do once we get through transfer functions and impedance. What's up?
Okay, so like whenever it comes to time domain responses and loss transform, essentially it's like they feel like the same thing except using the P as opposed to an S. So what exactly is the difference together? Like why would we choose why would we choose a loss over that time domain?
Because the Laplace transfer function is actually the real transfer function, and the time domain one was one that we kind of made up to be popped up like the other.
Okay, so like the Laplace is actually what would be used out in a while.
Yeah.
But the time domain is just a way for us to kind of make sense of it in our head by using knowledge we already know.
Right.
Okay, gotcha.
Residue. Yeah, it's French now. All right. Thanks. Take it easy. See you.